So what about the reactivity of a carbon-hydrogen group as far as substitution elimination goes? If we could get the carbon, say, negative, that would be great. It could act as a nucleophile. If we get it positive by having an electron withdrawing group, it could act as an electrophile. But when we pair carbon with hydrogen together, that's a nonpolar bond, and it doesn't really have any reactivity associated with it. To really get that reaction to work, you would need to add, say, a radical, and you'd be moving through radical mechanisms. And that is one very active way to get just a pure alkane to react. The alternate fashion, or the alternate way we can do it, is we can bring this alkane near another functional group. So we're not looking at this new functional group's chemistry. What we're still focusing on is that carbon-hydrogen bond of the alkane. We're saying, what does that new functional group do to the chemistry? So what we mean by that, well, let's go through and look at a potential example if it would work with me. If it would work with me. There we go. Let's see if we can now alter that structure. Instead of having CHs in the middle, I want to make this a carbonyl. And so again, before you start pushing, well, the carbonyl, carbon, oxygen, I don't care about the carbon-oxygen reactivity. I care about the reactivity between this carbon and this hydrogen. Right? That's the functional group we're concerned about here. And it is a very important aspect that we need to be concerned about. So we might go through the process of saying, well, that's not relevant. And that stupid black box is going to stay there because, when you distract yourself, it's not relevant because it shouldn't affect it, right? Because that carbonyl isn't relevant. But by that same token, then, if I took an alcohol, an OH, and I put that near a carbonyl, then it shouldn't affect it. Well, that now becomes a carboxylic acid. This hydrogen becomes vastly more acidic because of its proximity to that carbonyl. Well, why? Why is it that that hydrogen becomes more acidic? Well, if we remove the hydrogen, helps if we draw what we were focusing on, we would put electrons on that oxygen. That negatively charged oxygen may not be great at stabilizing it, but with the power of resonance, can stabilize. So is that same contributing factor something that could help explain or change the chemistry of the carbon-hydrogen? Well, let's think about it. If we removed that hydrogen, what would our structure become? Well, we'd have a negative carbon. And this is where we might be screaming, well, negative carbons aren't stable, we can't form them. Before we get too excited, we should also evaluate the power of the resonance. There is a resonance contributor. That resonance contributor puts the negative charge on the carbon, on the oxygen, not on the carbon. Is a negative carbon okay? Well, yeah, it's not great. Reference our alcohols, but we can do that. That is a stable structure. So what does that mean? If we have a carbon-hydrogen bond next to a carbonyl, that hydrogen becomes acidic, and it now introduces a whole new world of reactivity. That whole new world of reactivity is something that we have already addressed, and we'll look at here in the next slide. I've kind of highlighted a little aspect of that to help draw your attention to it. So we've seen this before with our enols and our enolates. If we were to go through and run the mercury reaction or the mercury addition, which H3O plus to an alkyne, that pi bond does go through the addition reaction, and it results in the presence of the OH and a new H on our structure. Right? So that's cool. But because we still have that pi bond, we're now susceptible to potentially more chemistry. That chemistry is that I have an alkene and an alcohol in an overlapping environment. This is where we get the term enol. Okay? That enol, as we learned back with the mercury structures or the mercury additions, is unstable, and it very quickly reverts to the ketone form in this particular case. If we did it with boron or a borane reaction instead of mercury, what functional group would we end with? hopefully you were able to get that question right. So as we continue on, so we've got this ketone sitting here, and that ketone has accessible chemistry. That accessible chemistry is that these hydrogens are mildly acidic, and acidic, for the record, is AC, not AL, is acidic. We can take advantage of that chemistry, and that's where we get keto-enol tautomerization. Ketones under acidic conditions can move to become enols, and ketones under basic conditions can move to become enolates. Okay? The enolate tends to be a little bit easier for most people to see and work with, and that's largely because we have the negative charge there. The nucleophile presence is pretty apparent. Okay? We have a negative charge on our structure. If we went through to show a resonance contributor to this, we could show that we would put the negative charge on our carbon, and we now have two potential sites for nucleophilic characteristics. Which of those is going to be the best Lewis structure? Well, the best Lewis structure is what I've got labeled as our enolate, and the most useful one would be the one with the negative charge on the carbon. Best because we've satisfied octets and we've put the negative charge on the atom most likely to hold a negative charge. Useful because oxygen is going to be better suited to not have that charge on it. It's not going to be reactive. The ketone is the more stable form of this. So what we've now identified is the high likelihood of a nucleophile. That nucleophile is just as present in the enol. It's just not quite as obvious, because if we tried to go through and push this out to draw a resonance contributor, the resonance contributor for the enol is very, very, very unstable because it is doubly charged as opposed to singly charged. Right? Both of them are accessible, both of them are reactive. So you do have to be aware of both of them. Really, the big lesson to pick up out of it, though, is that you end with a nucleophile at that carbon, right? Which is often referred to as the alpha carbon to a ketone. So alpha being the next carbon to the functional group. Okay? So what do we do with it once we've got a nucleophile? Okay? Well, that nucleophile can now undergo all sorts of substitution reactions or other things. Okay? And in particular, what makes this really fun and interesting is that this is a carbon nucleophile. And carbon nucleophiles are very difficult to make because they don't hold negative charge well, because they're not electronegative. So cool, we can now react this nucleophile with a myriad of other species. Okay, we could react it with hydrogen, in which case it's just an acid-base reaction, and that's pretty boring. That just takes us back to the keto or carbonyl form, and we're back where we started. Halogens work great as electrophiles, right? And that's probably one of the trickiest reagents I've seen and students stumble on, is the elemental state for our halogens is an electrophile. Okay? Remember, those electrons withdraw away, making this bromine very partially positive and susceptible to nucleophilic attack. Carbon, great as an electrophile. We saw that with our halides, oxygens, nitrogens, carbonyls, which we'll see in future units. We haven't achieved them yet. Nitrogens aren't really good electrophiles because, again, to become electrophilic, you have to have something withdraw electrons. So if you look at everything above, hydrogen, halogens, and the carbons, all of those have something withdrawing electrons. Withdrawing, withdrawing, withdrawing. All of those atoms are withdrawing electrons from our kind of desired atom to react. And that's what's causing that reactivity. To get a nitrogen to be electrophilic, you would have to attach it to something that's more electronegative than it. And that just happens to be kind of challenging to do. Right? So we won't encounter those this semester. 90% certain of that. Oxygen is also an exceptionally rare electrophile, but where we see it show up, we've already seen, is in that peroxy bond. That peroxy bond is what's allowing that differentiation in electrons, okay? And that's gonna make, whoops, I drew that arrow wrong. That's gonna make our oxygen here very electrophilic, okay, or positive. And that's not due just to the oxygen-oxygen bond, it's also due to the secondary resonance stability of that whole piece, right? Effectively a leaving group. So where we're going to end up moving now is we'll take this new nucleophile that we've now discovered and just react it with all of these things and see what happens, because that's kind of what we do. We introduce a new reagent and we just run with it, smack it against all these different things and see what happens. So the easy reactions of our enolates are straight nucleophiles. We'll do our standard substitutions. It can form from either the enol or the enolate, but we typically see it as the enolate, and we'll see that that is actually a false statement almost immediately. Okay, so let's go through and look at our enolate structure first, because that's the easier one to evaluate, even if we don't always use it. That enolate acts as a nucleophile, right, which means all we need is an electrophile to perform that substitution reaction. So if we go through and look at the reaction shown down below, we've added sodium hydride, which is a fun base, which we'll see in, I think it's going to be 2 videos, and we're going to discuss it. But this is a very strong base. Okay, and I'll even add the very. We'll actually reference it as stupid strong. A stupid strong base, it will go through and deprotonate, remove that hydrogen. Technically what we're showing here is bad because that's not the best Lewis structure, that's just the most useful one. So if we were to go through and show this, what we would be better served to do as far as a mechanism would be to actually show this structure. And that's a little bit more representative. We should acknowledge when we draw out a mechanism that that chemistry is still there, and we should be showing the resonance to dictate how this is going to react. So now what I want to do is throw in some kind of electrophile. Right? Well, what electrophile are we going to pick first? Well, we'll pick the standard electrophile that we've been using first for a lot of our reactions. We'll pick our halogens. So those electrons can come out, attack the bromine, kick the bromine across. We would get the bromide popping off as a leaving group, and we would now get the new bromine connected, and we'd have bromide floating around. And we've now done a substitution, a neat substitution because we got rid of a hydrogen and we replaced it with a halogen. This is extra cool because that carbon-hydrogen bond is not the easiest to break. Okay, remember, we're taking advantage of the enolate chemistry to really drive this. And we're now putting on a bromine, and that bromine kind of fits in our kind of standard first semester OChem wheelhouse. And so we could now run the reactions that we would expect from that position. Okay, and that's all kind of well and good. We could also run it with a carbon, just a standard substrate from our substitution reactions. I don't think I actually drew out the product, so hold up and we'll draw out that product. And this one becomes fun because we're now adding 2 new carbons to our structure and connected through that new purple bond. So what we've done is a carbon growth structure, okay, which is really, really useful because when we're going through and thinking about how we build things, most of the reactions we've looked at is just changing out functional groups. We haven't actually made a larger structure. Now we can start to make larger structures. With larger structures becomes more complexities, but that's why you're in second semester, not first semester. Okay, so let's go ahead and kind of push this a little bit further, and let's take a closer look at that bromine one. And note here I'm saying I lied. And what did I lie about? Well, what I lied about was that the enolate, the base formed enolate, was more likely to be used than the acid formed enol. Right? And why? Well, here's the reaction that sets us up for this. If we go through and look at this reaction, we just drew out the answer, and you might say, well, the answer was clearly that. Well, that's not the same thing. What happened? Right? Why did this all of a sudden change on us? Right? The product that we expected, right, was that structure on the left, right? Just a single substitution, there we go. Right? Why did we end up with this thing where we have all of the hydrogens at those alpha positions substituted for bromine? Why not just once? Right? As an interesting note here, I've also provided in this kind of stepwise analysis an extra structure. I provided that starting material. And what this should harken back to in your mind is that when we talked about the amine chemistry and it as a substitution, we said that the amine was not a good nucleophile for standard substitution reactions. And we said it wasn't good because it had the potential to continue to react. Right? Are we in a similar situation here? So if we consider our starting material versus the product formed, and all in comparison to our starting reactant, H-, which was a stupid strong base. We'll just call it a stupid base. If we're going to analyze and think about this, if the reaction didn't stop once, that meant very significantly that it had to have been more reactive than our starting material. Had to. Well, what did our starting material act as first? What was this clutch step? Acted as an acid. So if our expected product didn't actually stay there, what we're saying is that that expected material has to be more acidic than this one. Why? Okay, so let's draw on a hydrogen. Why is that green hydrogen more acidic than that purple hydrogen from our starting material? Hopefully what you can acknowledge is that we have an inductive effect. As soon as we've put that halogen on there, that halogen is now withdrawing electrons from the carbon, which then makes each of the hydrogens connected to that carbon that much more acidic than our starting structure. Since we're under basic conditions, the base will now react with the strongest acid, forming a different active nucleophile. That different active nucleophile is now with the negative charge there. And now what happens? Well, that undergoes another substitution reaction, putting two bromines on. Once I have two bromines on, how does that affect the remaining hydrogen? Well, that remaining hydrogen is now that much more acidic and that much more likely to undergo the acid-base reaction. So what ends up happening under basic conditions is that any alpha hydrogen gets replaced, right? And so we have to be kind of cognizant of that when we go through and pick these halogenation reactions. The acid conditions, though, actually fix this problem, and we don't get multiple substitutions. Of course, the question then becomes, why? Right? That's a challenging one. So what we should do is first address the chemistry going on with this. Right? In our first step of this reaction, we have our starting carbonyl, we have our electrophilic bromine, and then we have our acetic acid. Well, it's acidic conditions. The most reactive thing here is H+. So the very first step of this reaction is that our ketone reacts with the H+ to become positively charged. Well, it doesn't like to be positive, so what could happen? It can do a resonance contributor to withdraw electrons. That carbon doesn't want to be positive, so what it can do in a small amount is it can deprotonate to form our active enol. The enol can now undergo the reaction. The electrons can come out, react with our bromine. okay? And that would get us to that first product, okay? So we have to think about these stages through the course of the reaction. So if we now go back and consider our acidic conditions, after we run the reaction one cycle, we would have starting acetone, and then we would have, and why not, let's add a dash of color here, our first substitution. Considering the mechanism that we addressed below, under acidic conditions, the first step needs to be to protonate that acid, or sorry, protonate one of our structures, either the red structure or the blue structure. Well, which one is more likely to react with the acid? Well, of course, the stronger base. Which one's the stronger base, red or blue, and why? The blue one becomes a weaker base, okay? Why is that? Well, remember that bromine is withdrawing electrons, right? Because it is withdrawing electrons, that carbon starts to become positive, which means it withdraws electrons from the other one, which means our oxygen's electrons get drawn into the structure. To act as a base, the electrons must leave the structure. In this case, as soon as we put the halogen on there, we've actually made the structure less basic. Because it is now less basic, it is less inclined to react with the acid, in which case the only reaction that can happen is our starting material reacting through to go through and create our intermediate, which can then shift off the cascade of mechanisms drawn below. Okay, so the acidic conditions fix this because when we halogenate under acidic conditions, we actually make the product less reactive than the starting material. And it is that secondary reaction that you need to be aware of and thinking about when you go through to explain these processes. Okay. This is going to show up again. So this is kind of a foreshadow for a future lesson, but I do want to address it here. The alpha halogenation reaction can be coupled in certain circumstances to be combined into what's known as the haloform test, okay, or a haloform classification test. We talked about the Lucas one earlier in one of the earlier videos in this unit. We now have a haloform classification test. Methyl ketones can be converted into carboxylic acids using halogen and hydroxide. Well, the halogen and the hydroxide are our standard for our alpha halogenation, right? The hydroxide is used to deprotonate. So we would get a deprotonation, which gets us our active nucleophile. That active nucleophile can then undergo substitution reaction with our electrophilic Br2 and set us up with the now substituted structure. Because we are under basic conditions, that reaction doesn't stop and we move all the way out to the position where those are all bromines. I'm going to fix that in a second. All bromines. The haloform test is actually another step after this. This other step after this, and this wasn't addressed on the previous thing, acknowledges that the chemistry of that carbon is quite positive. Right? Add to that the carbon out here is now desperately looking for electrons because each of those bromines is withdrawing electrons. So what ends up happening is that carbon can withdraw the electrons. The blue one can steal electrons from the purple one. It's not the greatest leaving group, so it does need to be helped. So we would need a nucleophile. If we evaluate at this point, we've used up all of our ketone nucleophile, so we have our enolate nucleophile. So the only thing left would actually be hydroxide. The hydroxide can come in and attack. And through a sequence of mechanistic steps, so multiple steps, not necessarily three, we run a nucleophilic, nope, I had that right, addition and elimination. The mechanism we'll learn later in the semester, so don't stress a whole lot about it. But what will end up happening is we will both add and eliminate to now get that substitution. We would get the remaining carbon with the 3 bromines connected to it. That carbon would be negatively charged. It would pick up the hydrogen. The electrons would shuttle to our oxygen, okay, which would mean we wouldn't have a carboxylic acid, but that's why we have step 2. And step 2 adds that last hydrogen to get us back to the carboxylic acid. This is typically not used to make the carboxylic acid. What this is typically used to do is to note what happens here. Okay, we're in hydroxide. Right? Hydroxide is aqueous. That reaction that I've circled in blue goes through and forms HCbr3. In this case, it's known as bromoform. Right? If we had chlorines, it would be chloroform. We had iodines, it would be iodoform. And one characteristic that all 3 of those have in common is that they are not particularly soluble in aqueous environments, which means if I add just a little bit of sodium hydroxide and one of these halogens to an unknown compound, if all of a sudden the reaction becomes cloudy, that cloudiness is due to the formation of this haloform. What does that mean? Well, that then tells me that whatever my unknown starting material was had to have a carbonyl with a very particular methyl group next to it. And that's where we're seeing the reference to methyl ketones. Okay? So it classifies, it allows us to identify an unknown compound or some characteristics of it. And that's why it's kind of nice. Again, spectroscopy and the relative drop in costs of both spectroscopy and the increase in costs of dealing with chemicals and waste starts to make this kind of a balance. And while if you don't have access to the expensive spectroscopic equipment and you need to run a quick test to learn something about your structure, this would work. A haloform test would work. Okay, because it was used again in this kind of classification system, it now becomes something that chemists as a whole have decided to test students on. Do you understand the logic behind it? And that's really what we're pushing for. It's the same thing that's getting pushed for in spectroscopy and most of organic chemistry. That is what is the logic? What is the process by which you're achieving this knowledge? So where this can show up is on an ACS question, which compound will give a yellow solid HCl3 when mixed with iodine and sodium hydroxide, right? What you're being asked to kind of do here is to acknowledge the reactivity of iodine. Elemental iodine is an electrophile. You're being asked to acknowledge that sodium hydroxide is a negative, is a strong base and nucleophile, and that somehow you are forming as a product a carbon with 3 iodines connected to it. Okay? So how would they answer this or show this? There's a variety of ways that it can be shown as a multiple choice. One way is just go through and be like ketone. I know it's going to sound stupid, but methyl ketone, aldehyde, and then carboxylic acid. Okay, so they could just give you the name of the functional group. They could also draw out the structures. So there's a ketone, there's a methyl ketone, there's an aldehyde, and here's a carboxylic acid. Okay, so if you just memorize that for this classification test, it's a methyl ketone, now what you're looking for is anything that has just a CH3 next to a carbonyl, and there you go, there's your answer. Otherwise, what you have to acknowledge is that the base would need to deprotonate. So where do we have acidic hydrogens? There's acidic hydrogens here, 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 and here. Right? But then I need to put iodine on because iodine is an electrophile. When I deprotonated, did I make an active nucleophile? Yes, 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 yes. Not good enough. or really not, okay? And it's not because of resonance, okay? So then it comes down to our product. Our product had a carbon with 3 iodines connected. Well, which of these would be able to put 3 iodines on? Okay, well, this has 2 hydrogens, 2 hydrogens, 3 hydrogens, 2 hydrogens, 2 hydrogens. Okay, so the only one that would allow for 3 iodines would be the methyl ketone. So you can reason your way through this, but you have to be aware of the chemistry. Otherwise, you just strictly brute force memorize it, and that's fine too. Okay, I will say that I definitely encountered this on an ACS test a long time ago, and I had no idea what they were talking about, and so drew out the reactions. So I had 4 reactions drawn out, and that's how I got the answer right, was exactly doing this. Problem solving based off the information I had at hand. It takes time. You have to be comfortable to accept that you're going to spend the time to draw it. If you accept that, then you start drawing right away, and that is my recommendation when you get to these. Apologize, because that was a bit of a lengthy video this time around. So yeah, good job. Thanks for listening. And we'll go ahead and stop this one correctly this time.